Hello ladies, so let's take a look at these two new theorems. One is called the mean value theorem, and then there is a specific case of the mean value theorem called Rolle's theorem. So let's start with the general one, mean value theorem right here. So what we see is that we have a curve and then we have a straight line between 2 points. So I have this point right here, point A, and I have this point right here, point B. And so for the sake of labeling our points, we know this point right here is A comma f of x, f of A, which means I need to plug in A to find the value. Whereas this point right here is B comma f of B, right? So essentially that's your x value and your y value. Well, what we want to take a look at is we need to make sure two conditions are true. Number one, we want to make sure that f is continuous. So as a reminder, that means we can't have any holes, jumps, or gaps. So if you take a look at this, I notice I don't have any holes, jumps, or gaps. We also have to make sure that this is differentiable. So that means we need to make sure that there's a derivative along this curve. So if I take a look at this function, it says if these two things are true, then there has to be at least one x value in between A and B such that this function right here is true. The derivative of f prime of c is equal to the slope of this point right here, these 2 points here. So what we're going to do is we're going to find out our f of b, our f of a, and then plug it into the slope formula. And what this is telling us is there then has to be some point on this graph, I don't know where it is, I'm going to estimate it's here, that has the same exact slope as the slope between these 2 points. Okay? Which makes sense. If there's a line right here, I know that there is a parallel line, I can draw a parallel line to it. And if I draw it at the right exact point, I will find that point C. And so what you're going to get instead is a point right here that's in between A and B that has that same slope. So that's the goal that we're looking for. Okay. There's a specific case of the mean value theorem called Rolle's theorem. And in this case, what we're going to notice is the value at A and the value at B is exactly the same. So here, A comma f of A and B comma f of B are 2 points that have the same exact value. If I then connect these dots, I notice that I'm going to draw a horizontal line. Well, what do we know about horizontal lines? Good. We know that the derivative of a horizontal line, or the slope of a horizontal line, is equal to 0. So in this case, what we're going to see is number one, I still need to be continuous. Number two, I still need to be differentiable. But now there's a third condition that says when I plug in A, when I plug in B, they have to be the same. So if all three of these are true, then I can use this equation right here. F prime of c is equal to 0, which means there has to be a number in between A and B where I will have the same exact slope, and in this case the slope, it has to be 0. And what you'll notice is this is a very important piece, because what do you notice about every time I have a slope of 0? It means my derivative is equal to 0, which usually means it's a critical point, which then means it could be a maximum or minimum. So this is how it kind of ties into everything that you've been working on, just in a different view. So let's actually see how these problems can be solved. You are going to need a lot of the space that I've given you. There's a very small amount of space in that section, but just go ahead and follow along. The first step is to make sure that all your conditions are met. So according to the directions, it says, determine if the mean value theorem or Rolle's theorem applies to the function on the given interval. If either apply, find all values of the c that guarantee the theorem. So if you notice, the condition 1 and condition 2 are the same for both mean value theorem and Rolle's theorem. Rolle's theorem just has that extra piece that they have to be equal. So I have to check all of these. So part 1 says I need to find out if it's continuous, right? So let's write down our 3 conditions. Number 1, our first 2 conditions is 1, it has to be continuous. 2, it has to be differentiable. F prime of x is differentiable. So to find out if something is continuous, I have to make sure I don't have any holes, jumps, or gaps. So in this problem, I know that I can always get a real answer as long as this inside is 0 or greater, right? So what we're going to do is we're going to find out and make sure that this interval counts. So I'm going to say x minus 1 has to be greater than or equal to 0. If it's less than 0, we know we have a negative number in the square root, and we know that's imaginary, and we don't use those in this class. So when we solve for this, we notice x has to be greater than or equal to 1. So I check my interval, and I notice everything is either 1 or greater. So number 1, I know I'm continuous. F prime is differentiable means I need to find out if the derivative works at all the pieces in here. So what we're going to do is we're going to take the derivative of the function right here. So I notice f prime of x is equal to the derivative of 4 is 0. If I were to rewrite this, I know the square root of x minus 1 is the same as this, so I know I have a 1/2 parentheses x minus 1 to the negative 1/2 times the derivative of the stuff, which is 1. And because I need to find out if this is differentiable, I am going to rewrite this with the correct denominator. So now I have to make sure that this derivative exists for our interval. And once again, I notice I have another square root. So this time I have to make sure x minus 1 is greater than 0. How come in this problem I use greater than or equal to, but in this one I used greater than? Think about where the square root is. If you notice, since the square root is in the bottom, we know that our denominator can never equal 0. So I'm going to set this so x has to be greater than 1. And if you notice, our numbers 2 condition says f of x is differentiable on open parentheses a comma b close parentheses, which means I can still use this because I'm greater than 1 but I'm not equal to 1. Okay, so according to this, condition 2 has been met. So the last condition that we need to check is condition 3. So I'm going to write that. I know this is a bit skewed. But condition 3 states f of a has to equal f of b. So to see if this works, I need to plug in my 1 and my 5 into the equation to see if it works. So if I plug in 1, f of 1 is equal to 4 plus the square root of 1 minus 1 is 0, which gives me an answer of 4. If I plug in 5, I get 4 plus the square root. 5 minus 1 is 4. That gives me 4 plus 2, and that gives us 6. So according to this, does f of a equal f of b? No, so I know in this problem, and let me scroll down here, in this problem, 1 and 2 were true, but 3 is not true. So the one theorem I can use is the mean value theorem. So what I'm going to do is I'm going to take the equation and the mean value theorem and start plugging things in. So I get f prime of c is equal to f of b minus f of a divided by b minus a, which is a slope formula, right? And so if you take a look at your notes, f prime of c is our derivative. So I'm going to plug in our derivative, 1 over 2 radical x, but instead of an x, I'm going to put c since it tells me to plug in a c, minus 1 is equal to f of b we actually found above was 6, and f of a we also found was 4. And our b minus a would be 5 minus 1. So if we continue to solve this, and now this just all becomes algebra, we get 1 over 2 radical c minus 1 is equal to 2 over 4. We cross multiply, right? So what I'm going to do is I'm going to cross multiply here, then I'm going to cross multiply here. And what we see is 4 is equal to 4 radical c minus 1. I divide by 4 on both sides. And what I get is 1 is equal to the square root of c minus 1. To undo the square, I square everything. And 1 is equal to c minus 1. I add that 1 and I get c is equal to 2. The last thing I need to do is make sure that this answer, c equals 2, is in our interval. Well, thankfully, our interval is 1, 5, and 2 is part of this interval, so I know my answer is c is equal to 2. So let's do one more example, and then I'll have you guys do 2 on your own. We're going to do the bottom example on your page, which looks like this. And we're going to do the same exact methods. First step is I need to check that it's continuous. So to check if it's continuous, I need to make sure there are no holes, jumps, or gaps. We know a hole happens when I factor. I can't factor this, so there's no hole. I know that a jump happens when I have piecewise functions. And then I also know that I have an undefined or vertical asymptote if I have a denominator. But in this case, none of that exists. So we know part 1 is true. Part 2 is to check the differentiation that it exists. So I need f prime of x, and if I do that, I get 6 over 5 x to the, let's see, negative 2 over 5, because 3 minus 5 is negative 2 over 5. I rewrite this so it's in my denominator, x to the 2 over 5. And since I do have it in the denominator, I have to make sure that denominator can never equal 0. So what I'm going to do is set 5x to the 2 over 5 equal to 0. If I divide by 5, I get x to the 2 over 5 is equal to 0, and x has to equal 0. So what I do is I need to check to see if this 0 is in our interval. And if you notice, our interval says I have to go from negative 1 to 4. So since 0 is part of that interval, we can actually say that f prime is not differentiable. Differentiable at 1, negative 1, comma 4. Therefore, neither theorem applies. Which then means I can't continue the question. This justification statement tells me that I cannot use either of the theorems, so I would stop here. So I hope that works out for you. I'd like you guys to try the 2 problems on the right side of this orange packet, and then I'll put up the video that shows you the steps for that one. Thank you. Good luck.